The first application of beam on elastic foundation is assumed infinite beam subjected to concentrated load. What we want to derive for that, we want to derive deflection equation in explicit form, and then derive the slope, moment, and shear. Consider this figure here. Infinite beam subjected to concentrated load P at the middle of the beam, and x-axis, y-axis starts at this point, the location of x-axis here at the middle of the beam. Start with the general solution for the deflection curve of a beam subjected to transverse loading, as we derived and explained in the previous section. Y equal to, y is the deflection at any point, equal to exponential lambda x multiplied by constant 1 cosine lambda x plus constant 2 sine lambda x plus exponential minus lambda x multiplied by constant 3 cosine lambda x plus constant 4 sine lambda x. Start with this equation and apply the boundary condition. The boundary condition of this case is that as x approach infinity in this side or in this side, as it approach infinity, the deflection will be equal to 0. Here is the deflection, the maximum deflection at the middle, and at infinity will be equal to 0. This is the first boundary condition. The first boundary condition is that the deflection of beam equal to 0 as x approach infinity. To fulfill this boundary condition, this condition can be fulfilled only if in the equation above the terms connected to e to the lambda x equal to 0 or vanish or equal to 0. Here if we want to apply the boundary condition y equal to 0, to make y equal to 0, here y e to the minus lambda x equal to 1 over infinity, which is equal to 0. Therefore, to fulfill this boundary condition, this part will be equal to y, will be equal to 0. This implies that the second part will be vanished, and the constant c1 and c2 will be equal to 0. Therefore, the equation will be y equal to exponential minus lambda x times c3 cosine lambda x plus c4 sine lambda x. The second boundary condition is that the slope of the deflection at the middle will be 0, since the deflection here is the maximum deflection and the slope will be horizontal, and since the slope will be horizontal, it will be equal to 0. Therefore, y dash dy over dx is the slope at x equal to 0. Here at x equal to 0, x start from this point, at x equal to 0 will be equal to 0. So we have to derive this equation with respect to x and then replace x by 0. Here the derivation will be minus lambda e to the minus lambda x c3 cosine lambda x plus c4 sine lambda x plus lambda e to the minus lambda x minus c3 sine lambda x plus c4 cosine lambda x. Replace x by 0, we will get minus lambda c3 plus lambda c4 equal to 0 leads to c3 equal to c4 equal to c constant. These two constants c3 and c4 according to the boundary condition number 2 will be the same. We will recall them c3 and c4 as c. Now write the above equation as in the following equation: y equal to constant exponential minus lambda x cosine lambda x plus sine lambda x. Now we have to compute the constant. The constant in this equation can be obtained from the consideration that the sum of reaction force will keep equilibrium. Here is the beam subjected to force P, and here is the reaction, the soil pressure, the spring in the spring. This equation, this case, applying summation Fy for this case gives us P equal to Ky dx, Ky dx from 0 to infinity and multiply by 2 because of symmetry. This is one part from 0 to infinity. We have to multiply it by 2 so that to cover all the elements in the infinity in plus and minus. Ky dx equal to P. Ky dx is the reaction of the soil. Now 0 to infinity, Ky dx equal to P. From this equation, after some modification, we get Ky dx equal to P over 2. Now replace y, the deflection, by this equation: constant e to the minus lambda x cosine lambda x plus sine lambda x, and here cosine lambda x plus sine lambda x multiplied by e to the minus lambda x. Now integrate and solve by integration by parts. E to the minus lambda x distributed to this parenthesis cosine lambda x plus e to the minus lambda x multiplied by sine lambda x, and continue to solve these two parts. For every parts we have to compute the integration: e to the minus lambda x cosine lambda x and e to the minus lambda x sine lambda x. Integration by using integration by part. After completing the solution of integration by parts, we get the following equation: e to the minus lambda x sine lambda x dx equal to 1 over 2 lambda. 2kc multiplied by 1 over 2 lambda plus 1 over 2 lambda will be equal to P. From this equation we can get the constant equal to P lambda over 2k. Replace this constant in the original equation of y equal to constant e to the minus lambda x cosine lambda x plus sine lambda x for x greater than 0. Here constant shall be replaced by P lambda over 2k. This equation is the deflection of infinite beam subjected to concentrated load. The concentrated load is P, and this is the explicit form. We can use it to get the deflection at any point in the beam. To get the slope of the beam, we have to derive the deflection with respect to x, since theta or dy over dx equal to the derivation of y with respect to x. After deriving this equation with respect to x, we get minus p lambda square over k e to the minus lambda x sine lambda x. This is the slope, the second equation we need. The third equation is the moment. Moment equal to minus ei over d square y over dx square. Therefore, to get the moment, we have to derive the deflection 2 times. This is the first time we have to derive it with respect to x. Deriving this equation, d square y over dx, and then multiply it by minus ei. After derivation, we get this equation, and since k over 4ei to the 4th degree of root, the root is 4th degree root, equal to lambda, replace k over 4ei by lambda, we get ei over k equal to 1 over 4 lambda to the power 4, and replace ei over k or k over ei by this term. We get 1 over 4 lambda to the power 4 multiplied by p lambda 3 over k e to the minus lambda x cosine lambda x minus sine lambda x. Now we can write it in another form. P over 4 lambda here will remain on 1 lambda, 1 over 4 lambda p e to the minus lambda x cosine lambda x minus sine lambda x. This is the bending moment. Shear. To get the shear, the fourth equation, we have to derive the deflection 3 times and multiply it by minus ei. Or directly we can derive the moment, then we can get the shear from the differential equation of moment with respect to x. Therefore, we get q equal to minus p over 2 e to the minus lambda x cosine lambda x. Now we have 4 equations. The first equation is to compute the deflection at any point, and the second equation is to compute the slope of the deflection curve, and the third equation to compute the moment, and the fourth equation for computing the shear. Here 4 equations are in explicit form, and we can apply these equations for different questions of infinite beam subjected to concentrated load. These equations can be written as follow: y equal to p lambda 2k, instead of e to the minus lambda x cosine lambda x plus sine lambda x, we can replace factor a lambda x and e to the minus lambda x sine lambda x in the second equation by b lambda x. And for the equation of m, we can also replace this part e to the minus lambda x cosine lambda x minus sine lambda x by c lambda x. For the fourth equation, we can also replace e to the minus lambda x cosine lambda x by d lambda x, and we can construct a table for these factors for different values of x as it is found in many references. Many references presents the value of a and b and c and d to make the solution more simpler than using these equations to get these factors. These factors of lambda x can be obtained from each other since they are essentially all of the same type. Look for example to a lambda x. It consists of e to the minus lambda x. Also with respect to b lambda x and c lambda x and d lambda x. All of them also have a trigonometric function cosine lambda x or sine lambda x. Therefore, we can find the following expressions by using simple trigonometric transformation. The following expressions can be obtained. A lambda x equal to minus lambda minus 2 lambda b lambda x2 equal to beta c lambda x2 equal to 2 alpha d lambda x1, where lambda x1 equal to lambda x minus pi over 4, and lambda x2 equal to lambda x minus pi over 2. Lambda x3 equal to lambda x minus 3 pi over 4. Alpha here, alpha equal to e to the minus pi over 4 sine pi over 4, and beta equal to e to the minus pi over 2 sine pi over 2, and gamma equal to e to the minus 3 pi over 4 sine 3 pi over 4. One can obtain, for example, a from b or b from c or d from b and so on. Let us take the following example to show you how to get for example a from d. 2 alpha d lambda x1, alpha equal to e to the minus pi over 4 sine pi over 4. Replace alpha here with this expression. We get 2 times e to the minus pi over 4 sine pi over 4, e to the minus instead of d, since d lambda x equal e to the minus lambda x cosine lambda x, but here lambda x is lambda x2, lambda x1. Lambda x1 equal to lambda x minus pi over 4. Therefore, here instead of d lambda x1, e to the minus e to the minus lambda x1, lambda x minus pi over 4 cosine lambda x minus pi over 4. 2 times e, since here e, these are similar, e to the minus pi over 4 minus lambda x minus pi over 4, minus times minus, positive with negative, remains minus lambda x. Cosine lambda x here, by using trigonometric relations, cosine lambda x cosine pi over 4 plus sine the first lambda x sine the second pi over 4. Since cosine pi over 4 and sine pi over 4 equal to 1 over square root 2. And also with respect to sine pi over 4 equal to 1 over square root 2. 1 over square root 2, 1 over square 2 times 1 over square 2 equal to 2. 2 with 2 is gone. Remain e to the minus lambda x. E to the minus lambda x cosine lambda x plus sine lambda x. This expression equal to a lambda x. Other relations are in similar steps. We can get every constant, every factor of lambda x from other factor. We can also find the following differentiation of factors of lambda x. They are important in the next lectures. We find that the differentiation of a lambda x to the dx with respect to x, dA lambda x over dx equal to minus lambda e to the minus lambda x cosine lambda x plus sine lambda x plus e to the minus lambda x minus lambda sine lambda x plus lambda cosine lambda x, which is equal to minus 2 lambda e to the minus lambda x sine lambda x. This expression e to the minus lambda x equal to b lambda x equal to e to the minus lambda x sine lambda x. Instead of e to the minus lambda x sine lambda x, we can use b lambda x minus 2 lambda b lambda x. The other differentiation are in the similar steps. For differentiation of b with respect to dx equal to lambda c lambda x, and differentiation of c lambda x with respect to x equal to minus 2 lambda d lambda x, and also with respect to d equal to minus lambda a lambda x. Now we can use deflection equation and the slope equation, moment equation, and shear equation to draw deflection, slope, moment, and shear along the beam. For example, we can use the first expression of deflection, p lambda over 2k a lambda x. Generally, we can get the following shape. Here is the maximum under the p, and along the pile the deflection will decrease and nearly equal to 0. Also with respect to slope, we can use the following relation with respect to slope. This is the deflection, similar to the first. This is the deflection, and this is the equation of deflection. The equation of slope, we can use it to get the slope, and also the moments. We can use, for example, Excel to draw these figures by using this equation with different value of x. For different value of x, we can get c lambda x, b lambda x, a lambda x, and we can assume p any value. With respect to shear, also we can get the following figure along the beam. 4 figures we can get from the equations of deflection and slope, moment, and shear for the case of beam or infinite beam subjected to concentrated load.